Chapter 9, Communication Systems, Background. All of the details that we're about to cover in communication systems in this chapter can be tested in the following 3 chapters: wireless communications, digital communications, and optical communications. So do bear that in mind. Communication is the transfer of information. What we do is we have our information source, say somebody's singing, or binary alpha computer code. We then encode it in some way so that we can transmit it easily. So in wireless, that'll be modulating it to high frequencies so that we can send it long distances in air. And then it goes through something like air or a copper cable. We may need to use a repeater or a generator to kind of boost that signal if it's attenuating. I'll come to attenuation later on in this chapter. And we then use a demodulator or decoder to turn it back into the binary or the audio or whatever it is we are interested in. Transmission mediums come in many, many forms. This is the only slide you don't really need to make notes on. And we focus on fiber optics in optical communications, telephone and internet in digital communications, and radio waves in wireless communications. The capacity of a transmission medium is limited or set by 2 kind of ideas: the available bandwidth, so this comes down to the physical properties of the material, government allocation, and the channel bandwidth, because often we're trying to send multiple streams of information at the same time, and each of those streams needs enough space to operate effectively. The government allocation kind of feeds into that same idea. The government says, well, we want to allow 100 people to send their signals, so we'll limit you each to having 100th of the available bandwidth. So bandwidth of cables, got the twisted pair of copper cables. You do need to know that the twisting reduces the crosstalk, so that's the interference between the different signals due to electromagnetic radiation. And the telephone network has bandwidths around 100 kilohertz. Coaxial cable, which is usually used for computer networks, is about 20 megahertz. That is slight. Well, I should put the 20 megahertz in the next one. And fiber optics, much more higher speeds, gold standard, and you'll see a lot of them putting them in. They've just put them in outside our house. And you're going to be talking about up to 100 megabits per second. So the channel bandwidth, it comes with an equation. The number of channels is equal to the available bandwidth divided by the channel bandwidth. Kind of common sense. But please do label this on your data sheet and make a note of it, particularly in your notes. Probably on the key points, I would imagine. So let's have a look at a couple of questions. I would recommend you pause the video at this stage and attempt these questions yourself, and then watch through me going through them. So first question. The available bandwidth for frequency modulated radio is 87.5 to 108 megahertz. So in other words, that's 20.5 megahertz. You don't pick the high number or the low number, you don't add them. You need to work out the range. How much bandwidth do you actually have? And in this case, it's 20.5 megahertz. We stick that in the equation for the number of channels, we get 102.5. Now, 102.5 means we've got 102 full channels and a bit of a channel. Now, we can't have half a channel. We can't have 90% of a channel. So if you've got 102.9, that wouldn't be good enough. So we always round down. So that's just something to bear in mind. You're always going to be rounding down with the number of channels, just so you've got a full channel. The second example, coming from a slightly different angle, we're told the number of channels, we're told the bandwidth of each channel. Now, it's up to you. You can either take the equation and rearrange it, or you can put the numbers in and then rearrange it. Comes to much the same thing. So the cable bandwidth is the same as the available bandwidth. That's how much signal we can send down the cable. Same thing. and we would multiply the number of channels by how much they each need. So the minimum cable bandwidth would be 384 kilohertz. Any less, and you're not going to be able to send all the signals, which is bad, obviously. Okay, so how do we split into these different channels? So this comes to the idea of multiplexing, time division multiplexing, frequency division multiplexing. You do need to know TDM and FDM. So a common exam question is, what is FDM? What is TDM? And you grab the easy mark by writing frequency division multiplexing. Thank you very much. So time division multiplexing is splitting the signal into times. Frequency division multiplexing is splitting the signal into different frequencies. So let's look at time division multiplexing first. Probably easier to think about. So what you would do is you would send a bit of each signal. So you'd send a bit of the signal, then pause, send a bit of the next signal, pause, send a bit of the next signal, pause, and so on and repeat round. So you might be sending, say, bit 1 of these. So this might be bit 1, bit 1, bit 1, bit 1. This might be bit 2, bit 2, bit 2, bit 2, bit 2, and then bit 3, and so on. Now, in reality, you're going to send more than one bit at a time. But our decoder, the thing receiving the signal and transforming it back into binary or audio, whatever we want, often has a limited amount of time that it can process these things. So given it takes time for it to process it, you may well want to send a bit of the signal, give it some time to process, and then whilst that's going on, send a bit of the next signal. So there is an advantage of this system. Frequency division multiplexing. So this is where we give them separate frequencies. So I'm going to give you a quick sketch, and we'll look at a concrete example in a second. You don't need to draw the sketch. So time. So what you would do is you would send all of the signals at once. These should all be straight lines. This is a rubbish sketch, but you get the idea. You make sure there's a gap in the middle called the guard band so they don't interfere with each other. Please don't copy this one, it's awful. And you get something like this going on. So let's look at a concrete example. So let's say you've got 3 radio stations, they've each got 8 kilohertz, and they've got a carrier frequency which is much higher. The carrier frequency is always going to be much higher because it needs a higher energy to be transported across large distances. That's why it's the carrier. In fact, the carrier is often in the megahertz range, whilst the information signals are in the kilohertz range, and we'll see more of this when we look at wireless communications. So we need a bandwidth of 8 kilohertz for the information. So we've got 80 plus or minus 4 kilohertz, or in other words, 76 to 84 kilohertz, which gives us that 8 kilohertz range. Now, if we look at the next one, we've got 90 plus or minus 4 again. So that gives us our 86 to 94 kilohertz, which is the sort of thing you hear on the radio, 86 to 94 FM and things like that. Notice there is a gap of 2 kilohertz on each one. You do need to be aware of these phrases, time domains and frequency spectrum graphs. So do make sure you've got both of these down in your notes. This is a time domain where we've got time, and you can see the 3 different stations and their 2 kilohertz gaps between them. Sometimes for us to draw it the other way around, so this is with frequency on the x-axis, not time. And this is useful when you're looking at frequency modulation and things like that we'll look at in wireless. So you can see, again, they've got 8 kilohertz and they've got 2 kilohertz band gap in the middle, guard band in the middle. Yeah. Okay, so how do we start to separate them? So what we need to use is low pass filters and band pass filters. And how do these work? Well, those are the main points about what they're doing, and let's look at that in an example to make sure you got these notes down. So what do we do? Well, we've got our signals, and any signal has a massive range of frequencies. But the important bit is the low frequencies. Those are the ones where 90-something% of the signal is the information is. So what we do is we whack a low pass filter on to start with to cut out those high frequencies. And the reason for this is that we then won't get interference because this is now limited to up to 4 kilohertz. So anything higher, it won't interfere with. So these are all low pass filters. And we then put them through some kind of modulation. And what this does is it shifts them. So this, instead of being 0 to 4, is now 4 to 8. And this one, instead of being 0 to 4, it's now 8 to 12. And we've separated them into 3 bands. We've got frequency division multiplexing going on, goes through our cable, and then at the other end, this is a low pass filter, but the rest of these are band pass filters. And this is all about cleaning up the signal, because anything outside that range of frequencies that you have got is noise. It's interference from other signals, it's noise from the environment. It's definitely not part of the original signal, so you need to get rid of it. And then a demodulator to make it sound normal again. Nice little question at the bottom here. So we've got this question, each channel has 4 kilohertz, and we've got bandwidth of 200 kilohertz. How many can we have? Well, obviously we stick it in the equation. The number of channels is the available bandwidth over the channel bandwidth, 200 over 4, 50. And we'll always round down with number of channels. Last thing to talk about is the data rate. How many bits per second can we send? For digital signals, this is constrained by the available bandwidth, the number of signal levels, and the amount of noise. Obviously, noise cuts down. The available bandwidth is part of it, so the more bandwidth, the higher the data rate. The number of signal levels is a multiplier. So if we are talking binary, then we would need to multiply by 2, because there are 2 signal levels, either 0 or 1. So this is an important equation. The maximum data rate is 2 times the available bandwidth for binary. This only works for binary. If it was, say, 4 signal levels, then you'd have 4 times the available bandwidth. We only ever look at binary because that's what we use. So let's have a look at this question. What is the minimum bandwidth required for a fiber optical cable to carry binary data at a rate of 30 gigabits per second? Well, so we've got the data rate is 30 gigabits per second, and we know that the available bandwidth only needs to be half this much because we're doubling it due to binary. So that will be 15 gigahertz. This bandwidth is measured in hertz. Data rate is measured in bits per second. And that's it. That's the end of this background to communications. Do make sure you got thorough notes. I know there are a lot of them, but they are all really important.